All right. Good morning, everybody. So I'll share the screen now. Let's just to walk you through the web page, just that we are literally on the same page. All right. So yeah, so this is the web page of our course. Maybe we can just quickly repeat that these are basically, here is an overview of how you can get your points. It's going to be a midterm exam or final exam, and then there are these important lab assignments that you should work on during the semester, and they are worth quite a lot of points. So yeah, so work on all of those in due time. Okay, then there is the lectures page where you have the overview. So today we are here and we will do adversarial search. Okay, so I asked you to watch this video from Berkeley, which is this one. So it comes from here. So there's in a couple of lectures we will do it in this way because these lectures are very good and they are taught by world experts and they are also very nicely done. So I think there's no point to reinvent the wheel, and we can instead make it more interactive during our lectures. There's also a more recent course here from 2018, so which is also linked from our web. So this would also have similar content, but for now I'm using those from this 2012, 13, 14. Okay, so let's make another poll, which is did you watch the lecture from Berkeley? Okay, so I'm not sure if you see the results now, but I saw them. So not many of you actually did. So that's not good news. Okay, so I asked you to watch this before the lecture, and I think it's good lecture, and we should do it like that also next time. So next time you have another link to for the expected marks, which we will do next time. And really, there's a lot of overlap with what we are supposed to do. So I really ask you to watch this beforehand and then come up with questions, and then we can really make use of it, that we make it more interactive and you come prepared, and we can discuss what you didn't understand. Okay. So so that's for this part. So I guess now I can switch back to the slides, and yeah, we'll go more quickly, right? Because the content is here online. So today, okay, I'll try to redo most of it, but please next time watch this really before the lecture. Okay, so adversarial search means that it's a search where you have an adversary. So in the search we did so far, we had an environment like a map or a maze or something, and we were asked to find the shortest path somewhere. So we had complete knowledge about the environment, and we also had complete control. So we were just looking through the state space to find the shortest path. So that was a relatively easy problem, of course, depending on the scale, size of the problem, but at least it was all up to us. What we're going to do today is we will have this adversary, so our opponent that is playing a game against us, which will make things more challenging. So let's dive into it. Maybe I can stop my webcam such that you get a bigger view of the slides, like this. Okay, if anything is unclear, just stop me, talk or write to the chat or something. So games. There's a lot of games, of course, and they've been quite important for the history of AI because this was kind of they were landmarks when AI could beat the, let's say, grandmaster or world champion in specific games. So we had the Deep Blue for chess, we had the AlphaGo for Go. Deep Stack is computer playing poker. So why games? Well, they are hard to solve in a way, but as we discussed in the first lecture, some problems in the real world are actually much harder. But so they are hard, but at the same time, they are the right problems for algorithms, because you still have sort of the uncertainty, let's say, is limited, and so you can nicely tackle them with computational approaches. And also it's kind of important, let's say, for the public, because when you really manage to beat the world champion in some game, then it makes a lot of publicity. The adversarial learning has become also there's also a new meaning to this now, which is associated with deep learning. And you may have heard of these GANs, which means generative adversarial networks. And this means that, now for autonomous driving, for example, you need to classify what is in the scene, where is the traffic light, where is the pedestrian. And the deep networks are actually doing really well. But what people found is that you can still trick them, that even if you make really, so these two images look identical, but they are not. And if you make the right tiny changes, kind of targeted changes to the image, you can completely basically change the way the network, let's say, classifies where, let's say, the road is or the pedestrians are. And it's called adversarial learning because you're kind of the adversary of the network that is doing, let's say, the classification. So that's a new sort of meaning to adversarial learning. Okay, so just like we did with search, the only way forward for us is to formalize basically the situation. So just like for search, we have some states. So here is tic-tac-toe. That's one of the easier games. So the initial state would be, where the circles and the crosses are. So that would be the state of the game. The initial state would be that the board would be empty. So we need to define the game as a sort of search problem. Then it's important, which player has to move here, because we have two players. Mostly we will consider two-player games today. What the legal moves are. So just like for search, it was like which roads lead from a particular town. Now it's which legal moves I can make in a particular state, in a particular position. And the result. So it's a transition. So it's a state. This is an action, and the result of a move. And terminal test. So before it was, am I in the goal? And now, is game over. So if it's chess, it's checkmate. If it's tic-tac-toe, somebody has these 5 in a row or on a diagonal. So these are sort of the components that we will need. And terminal utility. So you get a prize only in the terminal state. So basically, if it's checkmate, then you win, and that's so only those states have a utility. So during search, we could assign costs on the way, sort of how far did we, let's say, travel so far, cost so far. But here really the only thing that matters is the terminal utility. Did I win or did I lose? And then you sort of have to propagate that back up. Okay. And and what we are looking for is basically a strategy, a policy that maps states to actions. So there's different kinds of games. We will specifically look at zero-sum games, and that means that the players have opposite utilities. This can be literally zero-sum. I think in tic-tac-toe, if you win, you get a +1. The one who loses gets a -1. If you both get 0, so it actually sums up to 0. In chess, it's not like that. It sort of sums up to 1. But that doesn't make a difference. We still consider this a zero-sum game. What matters is that what I don't win, then all that goes to my opponent, which means that there's no point in cooperating. You have games that are more complicated, where it's a sort of trade-off between cooperating and fighting with your opponent, and then you need to find the right balance. But that's of course much more complicated to handle computationally. So in this case, we will deal with these so-called zero-sum games. So we will look at two-player games and turn-taking games. So it's my move, then it's the opponent's move, and mostly deterministic, so with perfect information. I have the position on the board, so I know everything, and if I want to move my king to by one square, it's just going to move there. Okay, so there's no uncertainty associated with the moves that I'm making. Some games, like poker, for example, are not fully observable. So because I don't know what my opponents have in their cards, and this makes it more difficult. But that's not the case for tic-tac-toe or chess, where basically you see everything. You have fully observable environment. You have complete access to the state. All right, this I think we discussed. Okay, so here's a game tree. So game tree means the different evolutions of the game. So with search, we had the search. We had a state space, like let's say cities on a map, and then we have a search tree. So here we have a game tree, which is like the state space. How the game could evolve, and then we again will have a search tree, like where we currently are as we search through the game tree. Okay, so it has these levels. It's always on let's say odd levels. It's me on the move, and on the let's say even levels, it's the opponent's move. Okay. Now, what is important is the value of a state, and it's formalized as follows. So I'm in a state S, and the value of that state is the maximum value of the successors in that tree. So basically, which means that I'm on the move, and from all those children, I have the possibility of choosing my move. So that's why I can max over the children. But then the tricky part is, going down the tree and actually choosing which branch will lead, which will be really the max. And yeah, as we said, the values are known only for the terminal states, which are basically the leaves of the tree. So the challenge is, just like with search, to basically work your way down, and then then you can basically go back up and see which branch to choose. So okay, so here is an example. So this means here that it's the move of let's say the max player. So we will sometimes call the players max player and min player. And so the max player can choose here which action to take, A1, A2, A3. And here is the level of the min player, who can choose from this node. He can choose one of these three actions, B1, B2, B3. The same here, the same here. And so on these levels, you're trying to maximize the number. These are the terminal values of the states. So whenever we get here, then me, so the player on the top, which is the max player, or the gets 8. Okay, so I play this, he plays this, and I get an 8. Okay, here I get a 12. So this is sort of good for me, but here I get only a 3. So now the question for you is, what is the value of the root of the tree? So what we consider that both opponents play, both players play optimally. What will be the result of such an optimal evolution of the game? So let's make a poll. A, B, C, D. So yeah, take your time to think about it. What do you think the right answer will be? Okay, so let's publish the results. So most of you think that the correct answer is C, which is VA equal to 2. So why would that be the case? So the 2, I assume you picked it from here. Now the question is, why would that be? So here it's player A to choose one of these. Here it's, so if we end up in here, then yes, the min player would indeed choose this, to get a 2. However, player A would not pick this branch, right? Because this 2 is not good for him, and instead what he can achieve is a 6. So the correct answer is A, because if I have the choice, I can go here, and then even then, if the min player does the best, he can get at most a 6. So basically, he has he has no alternative, and I will end up with a 6. If I went here, then he could get a 3. Here he could get a 2, but I would not go there as the max player. But instead, I would choose to go here, and I would get a 6. So the correct answer is A. Is this clear, or why did you get sort of fooled?
Sir, what about 16?
What about what? 16?
It's in C. Yes.
Yeah, well, 16. So the way this works is that on these levels, the max player is choosing the best for him, which is maximizing. On these levels, the min player is choosing, which is minimizing. And if I, as a player A, or if I, as the max player, go here it's the choice of my opponent, but he would not choose 16. That's not good for him because he's minimizing. He would choose a 3. So he would choose to go here. So when we propagate it back up, I would end up with a 3, but that's not my maximum. Instead, I prefer to go this way and get at least a 6. Is that clear? Because I cannot assume that my opponent is a fool. Instead, I assume that he plays optimally, and so that's that's basically how this works. Which is a reasonable strategy, right? I mean, of course, you may have reasons to believe your opponent is a fool, but it's risky. So, and also for our search algorithm, the sort of best choice how to program this is that we assume that both want to maximize / minimize their outcome, their utility. You see why the 16 is not the right solution there?
Yes, it is now. I just thought the word was different.
Okay.
May I also ask a question? Why can't we choose the D option then?
Because here as the max player, we would end up with a 2 because the min player, when we get here, would choose this way. So he would get a 2. And that would propagate back up. And 2 is not the maximum we can achieve. It's the 6 we can achieve here as the max player. Okay, you have to sort of get used to this switching of who chooses and who maximizes and who minimizes. But so if I choose A3, he would choose this way. We would get a 2 for me. But that's not best because my best option is as the max player is to go here, and I have at least a 6. So I get a 6 because assume that the main player also does the best for him.
So we have to choose a tree with the minimum mean losses. Yeah.
Something like that. Yeah. So basically, on every level, you basically flip sort of whether you're maximizing or minimizing, and we will see how that works as we proceed. But this was just to sort of start you thinking. So so I see that it's not like completely intuitive how this works. Shall we proceed? Is this okay for this slide? Okay. So 2-ply game, max for min. So this 2-ply. So there's, for example, in chess, one move means that formally consists of 2 plies, white playing and black playing. So you have to so that was this what this word means, 2-ply game. This is the same that we had, and now we can see it now basically in action. So one move consists of 2 plies or half moves. So I'm the player that starts, let's say in state A, and I want to decide what to play, whether A2, A1, A2, or A3. Now this BCD are the possible outcomes of my moves or my plies. Now the opponent is about to play, and the numbers here, they are the terminal states that denote my profit or utility. And how I evaluate the nodes, which means assigning the numbers to the nodes, that's thanks to this minimax algorithm, which we can now play. So I got here, and then this is the min player. He chose the 3. Okay, fair enough. Now let's try the other branch that I have to try. I cannot. So I can assign a 3 here because that's already clear, but I cannot assign anything here yet because I don't know. I still have to search through the rest of the tree. Okay, here we get a 2 because the min player is minimizing. Now I have to also look here, which is also going to be a 2. And now finally, I can assign a value here, which in this case it's the max evaluation, and it's going to be a 3. Right? Okay, so that's basically it's simple. You just have to sort of be cautious, whether you're maximizing or minimizing at a given level. Okay, so, and this is how you write it. So I'm going to choose the action as the max player. I'm going to choose the A1 action. And this is the way, how you can formally write it, because it's the argmax of the result of state A, which was here, and, over all the actions I can take, which is A1, A2, A3. Those are the actions I can take. And I want to take the action that gives me the maximum result as I dive deeper into the tree. And in this case, that's going to be the action A1. So that's for tic-tac-toe. So here I'm the max. I can play all these different moves. Then the min will put the circle somewhere. And again, so this is how it evolves. And this is the tic-tac-toe version 3x3. So when you have 3 in a row, you win or lose. And these are the terminal states, the leaves of the tree, where you can get the utility. So in this 3x3 tic-tac-toe, it's actually sort of doable that you compute, all the way through. But that's not the case for, let's say chess. Now, let's start, in pseudocode writing up the algorithm. So the minimax of state S, if the state happens to be the terminal state, then it's going to be just the utility of it. So, we have a terminal test, is this checkmate or is this, 3 in a row or 3 on the diagonal? If yes, that's our terminal test, then, we just assign the utility, which is this. That's when we get, all the way through to the end of the game. But normally, it's going to be what we saw before. It's going to be the maxing over actions and then running minimax on the result of the, so, okay, this might be a bit hard to read, but basically it's a recursive call, okay? So I'm at my, let's say, level, and I will choose the action that, from all the possibilities is going to give me, the most utility. If player is max, it's max. And if the player is min, which is on those levels, is the same thing, but he's minimizing. Okay, so again, it's a recursive call for the descendants, for the children in the tree, and the result of going from, let's say, this state over all these actions. But the min player chooses the minimum of these, the max player chooses the maximum of these, and that's basically that's it. So yeah, a recursive course is basically a sort of natural way of implementing this. And yeah, so to write it out in more details, yeah, this is basically the how you can fill in the individual components. This is the minimax of a state, and then there is the min value, and then there is the max value. So again, depends which player's move that is, and and you will initialize the value like this. In one case as plus infinity, and in the other case as minus infinity. So you're the max player, so minus infinity is the worst you can get, and you go over the actions, and as soon as you get something better, then you update your value. So that's how it works. And yeah, it's you can also see examples in the video from the Berkeley course. It's just that they do examples. They like to do examples with Pac-Man, and we don't do Pac-Man, so we do, for example, chess. Yeah, I also invite you to try it with pencil and paper to sort of work your way through, such that you really are sure that you understand. So you would follow this pseudocode, and then you can sort of see for yourself, how the workings of the algorithm are. So this is basically how it looks like in reality. That now you're filling the search tree, as you go through. So you just take one action, gets you somewhere, then your opponent does another action, and these are now the min player is going through all the options he has there, and now these were all the possibilities he had, and we can now assign this 3. We already seen this before. Okay, again, This is the min thing, so it's going to get a 2 up there. We've seen this before, right? And then you can put a 3 up there because the max will choose over there. So this is how it works. Does it remind you of any of these search algorithms we had? What is it similar to? Would it be a BFS or a DFS or?
It's like BFS because it goes like in levels.
Okay. Other opinions? No, actually, it's not. Actually, it's like DFS because you need to reach the iterative deepening. Well, we will get to that, but what we saw so far, it's not really iterative. We just, go all the way up to the leaves. So the point is that until I reach the leaf, I cannot know anything because I cannot get the utility there. So in search with BFS, I could sort of search through and I could still sort of make progress because I could compare the costs, reaching different, let's say, cities or different states. But here I cannot really make progress because until I see whether I won or lost, I just cannot see anything. So you have to really go deep. So it's DFS, and that's why I also talked about the recursion. So as soon as you see this recursive calls, this is one way of implementing depth first search. That you basically, you go down and then you call the same search on your children. You could also do it differently using that stack. That basically, the new nodes that you discover, they would sort of be on top, and then they will get done first. Yeah, I'm talking about the frontier, and then you would also dive deeper, naturally. But basically it's the same thing here. So you go, that's also how we saw this filled up. We first reached the leaf nodes of this branch, and only once we were done with it, we again dived into the next one. So BFS would work differently. It would first do these 3, but in this case, it's not really meaningful because you cannot do, you cannot assign any utilities. So you have to basically do a DFS-like thing. Okay, so it's a sort of exhaustive DFS, which also means it has the same exponential time complexity, which is b to the power of m, which is the depth, b being the branching factor. So it's okay, I can maybe write here. Is it not writing? Okay, that's right. So it's b to the m, m being the branching factor. The space complexity, we know of DFS. That's so this is in the O notation. It's going to be so the time complexity will be O B M, and space will be O B M, like this, which is much less dramatic. So this is the exponential complexity because you basically have to search everything, and the space complexity is better because basically as soon as I'm done with one branch, I can forget about it, and then I can go another branch because I already have sort of learned what I needed to learn, and I don't have to keep all this in memory anymore. So that's why it's just B times M, which basically signifies, I'm sort of doing one branch at a time. Now for, let's say, chess, the branching factor would be equal to about 35. So what does that mean? That B is 35. What does it mean that the branching factor is 35? What does it mean, let's say, for chess? Any ideas? Or maybe it's trivial. Well, it just means that on average, in every position of the board, there's approximately 35 legal moves. So 35 moves or plies to consider in every position, which is a lot. So, in this, toy example we have here, branching factor is 3, right? So imagine you have 35 instead of that. And the depth for chess, okay, this is about 100. So 100 plies, all of these half moves, or 50 moves if you count it, white and then black. So that's sort of the, let's say, average depth until the game ends. There's a checkmate. So you can imagine that this is really a huge state space. So there's no way you can compute, exhaustively till the end. Okay. So we cannot dive to the end. So can we save something? Is there a way to save something?
You mean ways to save time, or?
Yes.
Yeah.
Exactly. So, if you look at this tree, is there any nodes that you don't have to go through for some reason, that you just, there's no point in looking at them, you will not lose anything?
I've got an idea. For example, we can go through the half of the depth, and after that count the result from on this stage and choose the best one, for example.
Not sure I understood. Can you say again? Or I can also allow everybody to draw here. If you just can mark what you think you can just skip, for example, or
my idea was if we have, an endless number of these stages, of these trees.
Mm-hmm.
So we can, and we have no possibility to count all the, all the possible trees result till the end. So we can at least walk through the half of this interval and count the best result for it. I'm not sure if it gives an extremely positive result, but maybe it makes some sense.
So would this be a sort of a kind of heuristics, or would it,
Yeah. Yep.
Okay. I see. Well, I also saw, I didn't pay attention to who was drawing these things, but that seems like a good solution. So maybe somebody who actually watched the lecture, or maybe somebody who is very smart can you explain, why is this is actually correct? Why do you think we could actually not look into these two?
I did it because, for example, if you share these notes for the first time and you find the number 3 is the like the minimum one, and then go and you find 2, you don't need to look at this rest because 2 is less than 3, so it's going to be like minimum. So
Yes.
you
yes.
can, so the result is going to be here, which is bigger than 1.
Right. Right. Wonderful. Exactly. So, and this is the essence what we will just learn, which is called alpha beta pruning. So this is very true. So imagine we look through the tree from left to right, and we now know that, so the Max, it's, he already explored the subtree, so he knows that if he chooses action A1, he's going to end up with a 3 at least, unless player B, the min player, is a fool, but we don't take that into account. Okay, so now, but we have also other options. So let's try A2, and then this is the min player's choice. He can get a 2, and we don't know what's going to be in the rest, but actually it really turns out we don't need to know, because no matter what's going to be here, it's not going to be the branch that player A, the max player chooses, right? Because he already knows he can get at least a 3, and here there's a 2. So these numbers may may be 4 or 6, but they may also make it even worse. But in any case, it's not going to get better than a 2 from the max player's perspective. So there's no reason looking. Okay, so here will be a 4 and a 6, so it's actually a 2. There might be also, I don't know, a 1 and a 0. In that case, it would be a 0. But I don't need to know, because I have a 3, and if I have 2 or less, I'm not interested as the max player. And this I can, so basically, I don't really need to go there, and I can save some time. And this is exactly what we will go look into, and it's called the alpha beta pruning of the tree. Very good, Elisa. Okay, this we discussed. Is it like DFS or BFS? The complexity we discussed. And yeah, now we're basically trying to do better. So yeah, already we can basically unfold this now. So initially, the interval for the value of this node is from -infinity to infinity, because we don't know anything. Okay, we start exploring, and this is the min player's level, and here he sees the first terminal node. He can already assign from -infinity to 3, because he's the min player. So maybe he's going to find something lower, which would be even better for him. But he can already put the upper bound, which is a 3. So that's something he already can have, something he sees. Okay, 12 is not updating that. I'm the mid player, so I'm still in the range -infinity to 3. And 8 is also not going to update that. So now it's a 3-3, so it's a 3 for this node, because now I have the information. And we can also update for the max player, because the max player now knows if I take this branch, I will get a 3. Maybe with the other branches, I will get even better, but at least I have a 3, which is guaranteed. Okay, so same here. So main player, okay, he has a 2. And this is what we already discussed on the previous slide. So we are in the range -infinity to 2, but the max player has already a 3. So no matter how this range gets actually updated, then he's not going to be interested, because he already has more than where this is going to end up, and that's the sense of the pruning. And yeah, same here. So got 14. So it's going to be this range. So we need to keep looking, okay? Because 14 would be actually good for me as the max player, right? And we can already, because now we have seen all 3 branches, we can already start updating this one. So now I know as the max player that what I can expect is in the range between 3 and 14. But I need to keep looking because here is the min player's node and he may get something better for him. But now he gets a 2, and now it's a situation like we had before, right? Because we are again in this range, and I stop being interested as the max player, and I can finally get my value, which is going to be 3, and I'm going to go this way. I don't care what was here and what was here, even if there was maybe a big part of the tree, because there's no point in going there. So that's the essence of alpha beta pruning. And practically, you can save a lot. You can save, depending on circumstances, maybe up to half of your time and the nodes you have to go through, which essentially allows you to go deeper in reality into the tree, which is a great thing, of course, which can make a difference, how good your algorithm is in that particular game. So yeah, so that's something that, and you will get the assignment, the lab assignment. Eventually you will have to program for the reverse game, a tournament player, and yeah, for you to succeed in that tournament, yeah, probably alpha beta pruning will be part of your solution. So it's called alpha beta pruning because we're cutting away parts of the tree, and alpha beta because we keep track of 2 values, alpha and beta, which allow us to actually, what we discussed sort of in common sense, why I don't have to look somewhere. This is the actual implementation that, if you work with these alpha and beta values, then you can actually just do the right checks and prune the tree. So this is, this probably you should sort of think about it in piece. So alpha would be the highest value choice found so far for any choice along max, something you sort of keep track of, and beta would be sort of the opposite. So as you go through, you keep updating these values, and those, by comparing against them, at the right moment, it allows you to do the actual pruning. So yeah, here you see the evolution, how that goes. So here you would set up the beta to 3. So that's the lowest value choice found so far for any choice along min in this particular circumstance. And now finally you can also assign the value, which is 3. And this propagates up, and on the level up, which is the maxis level, it will become an alpha. Beta would be still infinity, but alpha is sort of the minimum, the maximum value I found so far. Yeah, it requires a bit of thinking how this goes. But, yeah, I will not go through all the details, but it's just a technical thing how what we already discussed is implemented. And we will also see the pseudocode for this. Yeah, so how much can we save? That we discussed a bit. So as I said, in reality, you could save up to, let's say, half of your time, which is already a great thing. And how much you exactly save depends also how you consider in which order you consider your actions. So it can be sort of lexical ordering, or that you start from left to right. But you can actually do better. So if you sort of first examine, let's say, the critical moves, that are most important for for the game evolution, or for the outcome, then you can save actually much more, right? Because those are sort of the ones that are setting the extremes, of the evaluation of the values. So We will see some examples what that means in chess. Yeah, this is how you can see the how you see it algorithmically. So so there are these alphas and betas that you always update. Otherwise, it's sort of what we've seen before. And the new condition is that you're basically checking whether you go somewhere depending on the alpha and beta. So it's the minimax that we saw before, but in addition, you're updating the values of alpha and beta, and you're checking whether you should go somewhere based on the on these values. So that's basically saving you time. Okay, so now this was what was already mentioned, this iterative. So we had this iterative deepening DFS, and so the reason was that we didn't know how deep the tree is. So we tried up to a certain depth, and yeah, if we still had, let's say, time, we tried one level more, and so on. So the advantage here is that because if we really don't know how deep the tree is, or if we just assume it's going to be very deep, like in chess, we cannot afford to just unroll it until we reach the terminal nodes, because we will never reach that. And let's say time is limited. Let's say chess, you have, let's say, 2 hours for the game, so you just cannot afford that. So what you can do instead is that you compute up to like 1 move, 2 moves, 3 moves, 4 moves, and of course the time complexity grows. But the advantage here is it's also called like an anytime algorithm. That anytime somebody tells me, now give me the answer, then I have an answer from the level that I finished. In the meantime, I'm trying one level more, but in case I don't have time, then I have a solution already. So so this is actually convenient, and it's, since minimax is like DFS, then it's a solution that I can apply also here. And this wasting of resources, I think we discussed. So it's not too bad, because basically because of the way the tree is built, it's always that the most nodes, which actually cost the most time, are at the bottom levels. So the fact that I sort of repeat the initial levels, multiple times, doesn't matter so much. So in the end, it's about a factor of 2 that I'm wasting there. So so that's not too bad, and it's sort of worth the convenient thing that I always have a solution at hand. And so for alpha beta pruning, there's a bonus, which I can use the shallower iterations for node ordering, which means I already learned something from the level before, and then I can sort of reorder the tree such that I have now a heuristics which nodes. So this is a heuristics, okay? I just happen to think that it's probably good to search through some moves first. And yeah, but this can actually save me time. Okay. So yeah, it's a real-time decision, right? So this is iterative deepening. So, but the important thing that we are missing here is that what we discussed before, when we discussed that this is not BFS, but it's more like DFS, is that we can only know something when we are at the leaves, right? And now we're saying, well, you never can actually get to the leaves, and so that's when you need an evaluation function. So you cannot afford to compute until the end of the game. So at some point there's a cutoff, and you need to evaluate the board position. which has to be some function. So we will discuss some examples. So, so I have to stop there. I have to see somehow, whether I'm winning or losing, and that's it. Maybe I will have time later to compute, into a deeper depth, but for now I have to cut it here and, output a number that I can then propagate back up the tree. So yes, this is an evaluation function, and for all these games like chess or Go, you absolutely need that, because there's just no way you can compute till the end. Right, so you replace the sort of terminal test with the cutoff test. I cannot afford to dive any deeper, and I have to evaluate. Now, so what could the evaluation functions be? So it should be easy to compute, right? Because after all, it's, we want to save computational resources. So the evaluation function that takes ages to compute is not going to help us. And yeah, it has to be correlated with the chance of winning. So for chess, this is, the couple of obvious things that you just count the pieces, and there are these values, these kind of rule of thumb, 1 for pawn, 3 for knight, bishop, 5 for rook, 10 for queen. And, so if I have more pieces, then, I'm more likely to win. Then, if you achieve a certain level of play, there are some sort of fine tunings, so 2 bishops tend to be sort of a good thing, let's say better than 2 knights. If the position is open, especially, now knights are better in close positions. There's a lot of things that you should take into account, how the, like whether somebody controls the center of the board, pawn structure, and these all can be expressed as evaluation functions. And, but then you have, then you have a challenge to combine them, which, you will use some weights, right? This is quite an obvious candidate. So you would use some kind of weighted sum. So let's say you do it like this. How do you find those weights? So, you can ask grandmasters, you can ask experts, you can read literature, or you can use some machine learning to sort of find it for you. Or lately, you can also see the, for example, the AlphaZero, which is from 2017, which learned to play chess, Go, and shogi, and achieve superhuman level of play just by playing against itself. So that's a new way that you basically just let the algorithm play against each other, and then, using, let's say, a black box approach, figure out all the important weights by itself. And, that has been quite a breakthrough, that this AlphaZero was capable, that basically, it just by learning, so 24 hours of playing against each other, and it already achieved superhuman level in those 3 board games. So that's a new phenomenon, also associated with the progress in deep learning, in this case, deep reinforcement learning, that you can just basically learn this, without consulting any human experts at all. The problem with the cutoff is that if you sort of happen to do this evaluation in the wrong moment, it could have sort of disastrous results. So imagine my evaluation function is, counting pieces. So, these are the pieces that have been already, removed from the board. So they are the same. So if I just count pieces, the evaluation is going to be the same. But if there is white to move here, it's quite bad for him. So he will probably have to save the rook. But then, the situation is quite bad for him. There will be a check with the knight here, and it looks like a disaster for white. Instead, if white to move is here, he will just take the queen. So, this is a completely different evaluation. So just counting pieces in a position like this is not going to be very robust. So one thing that you should do is this quiescent search, which means applying the evaluation function only once things calm down. So, this is not the case here because there's a lot of things going on. There are pieces threatened, king is threatened. So it would be good to count just a little deeper in these kind of situations before I do the evaluation function, because in this case, counting pieces is really not telling you much about what is going on. So, so you can use these kind of things. And regarding the ordering of the nodes, the killer move, so-called, capturing opponent's pieces, check, should be considered first because they are likely to really dramatically change the evaluation. So, so these kind of heuristics can actually improve your performance quite a bit. Yeah, the same thing is horizon affected. So it's all about that there is a certain horizon when the cutoff comes. So in this case, the black bishop is lost, right? So basically he cannot go away. So the king might just go there and take it, and then yeah. So he has a rook plus, but it's not going to be as easy because there are these 3 pawns. But yeah, it's probably be sufficient to win. But if we imagine that the horizon is really close, only a couple of moves, then imagine that I move this pawn as a black on the move, check, and then the king takes it, and then move this pawn, check, and the king takes it, and then again here. So I just shifted and then I, let's say, count the pieces. And so my bishop will still be alive, right? So this looks like when by counting pieces, it's going to be better for me than if I don't do this series of checks, because within these 3 moves, my bishop will already be captured. So that's a sort of, that's a problem that if I really just do the evaluation function at the cutoff, and this is going to be the best solution. But obviously, this is not the best solution because I will just lose my 3 pawns, and I will still lose eventually the bishop. But it will just be beyond the horizon of my search. So that's a problem that I should avoid, right? I need to be aware of these horizon effects, that I'm just pushing something, let's say, inevitable beyond the horizon. But in the meantime, it's just gonna cost me 3 pawns, and I will not save my bishop anyway. So that's something to be aware of. Okay, so this is just to say that there was this famous match where Deep Blue defeated Garry Kasparov, but it's not to be interpreted in the way that computer really plays like Grandmaster. I mean, it could beat him, but it still plays, it's a completely different story. So it's still highly sort of dumb and brute force. So Deep Blue examined 200 million positions per second. And in some cases, he could achieve a depth of search 40 plies, 20 moves, which is really, really deep, right? And that's completely different than how Garry Kasparov was playing, because that's not really what Grandmasters are good at, right? So they would, of course, never consider 200 million positions per second. They would probably consider 1 position per second, or I mean, even less. And they would not, calculate so deep. So actually, they play completely differently. So they do use their, let's say, experience and intuition to do super effective pruning and evaluation functions. And Grandmasters only consider 2 or 3 moves in most positions, because they just know the others don't make sense in that position. So basically, there is a branching factor effective of 2 or 3 for them, while it's this 35 for the computer. So the performance at that time was similar, but the way they achieved that was completely different. Okay, and yes, so that concludes our lecture So questions. The textbook is this guy. It's this Russell and Norwich that you see here, at least for this part of the course. And you have the slides are already there. I'd also put the slides with notes where you have additional information on the web page, and the recording will also get up there. Questions at this point? So I will share the screen again, just to go back to our web page. So so here are the slides of today. I will also add those with notes, where you have that extra information. In Brute, you have the recordings of the lectures. There is also this YouTube channel where you can, that is linked from the web page, where you can also have the recordings, access easily the recordings of the lectures. And next time we will do games with random elements and multiplayer games, Expectimax. And so that's going to be, so the additional complexity will be that there will be, random elements. So here, we assume our opponent is perfect. And so we could basically, the search was easier because we could always, there was this rational opponent. But there are also games where you roll dice. And in that case, there's, this element of randomness where you cannot choose, what is, of course I can choose that the best on the die is a 6 for me, let's say. But in this case, it's not up to me. And then I have to basically consider all those alternatives. I cannot prune because I cannot choose, and my opponent cannot choose either. So that's going to be more complicated. And so before the lecture, really the content is going to be very, very similar to the lecture that is here. So I really invite you to watch this lecture from Berkeley, and take notes, come up with questions. And we will not redo this again. We will basically just discuss the content and dive into any issues that you may have. So for next time, please watch that. That lecture before you come to this lecture. Questions at this point?
Yeah, I've got a question. For example, if we have a game without specified result, something like oughts and crosses, if we have only 3 possible results, like 0, 1, and -1, that we had in this lecture. So what is the best way of finding the most optimal path in our game? So now we have to consider the minimum number of plies in this tree. Plies in this tree. Plies. Plies in this tree. Plies in this tree.